So today we're going to talk about relations, which is a new topic for us. So in math, we don't just talk about mathematical objects like numbers, functions, matrices, sets. In isolation, we talk about how they're related to one another. So we say that this number is less than that number, or this number equals that number, or this function is some other function's derivative, or this integer divides that integer, things like that. Right? So we don't speak of any particular mathematical thing all by itself. It's sort of, we look at the web of connections that it has with all the other mathematical objects. So informally speaking, for now, we'll say that a relation, and this is a very informal definition, will be more precise. I mean, our first sort of task is going to be more precise about what we mean by this. But informally speaking, a relation is a property of a fixed nature that is shared between pairs of mathematical objects of a specified type. So if you can't exactly parse that definition, that's okay. We're going to have a better one very soon, and hopefully the examples here will alleviate any potential confusion about what I mean. So the simplest example of a relation is probably equals. So you take, any subset, really any set whatsoever. It doesn't have to be a subset of the reals, as I've said here. It makes sense to talk about an element of that set being equal to another element of that set, right? We would know what that means. So now, looking at subsets of the reals, as I've indicated here, you could also consider the notion of two real numbers being less than each other, right? One being less than the other, or one being greater than the other, right? Or one being less than or equal to the other, or one being greater than or equal to the other. These are relationships that exist between pairs of numbers. So those are the most basic examples that come to mind when you would think of a relation, what a relation is, or what I'm trying to communicate with this definition of a relation. The second species of example that comes to mind that we've dealt with in this course is if we take any subset of the integers, those would be our mathematical objects of a specified type, then the property, so one property you might consider between pairs of integers is whether one divides the other. So, x divides y. We know what it means to say that x divides y. Another one would be that x is equivalent to y mod n, right? We know what that means. So those are some natural examples. And then you can also, as a general species of example, one can take the negation of any of these as a relation as well. So the negations of all the above are also relations. Right, so any two elements of a set, we can say that they're, know what it means to say that they're not equal. Any two real numbers, you can compare two real numbers and say whether they're not less than each other or they're not greater than or equal to each other. Any two integers, we could say that they, x doesn't divide y, or x is not equivalent to y mod n. So those are all properties that hold between pairs of mathematical objects. So our first task here is going to be, first task is to give a more precise definition of relation. Okay, so what do we really mean by this notion of relation? And so more pointed question, or well, so the pointed question that we'll ask. So how are we going to do this? We're going to ask, what do all the above examples have in common? So what do all the above examples have in common? And so to define relation, we're going to look at these specific examples and try and see if we can say, what they all have in common and use that sort of common notion as our definition of relation. So basically what any one of these things has in common is that what you do when you're looking at one of them. So think about like greater than, the relation greater than for two real numbers. So what happens when you're looking at this greater than is you consider two numbers, right? So you have two numbers in mind. You're looking at the greater than, and you put one of the numbers on the left and one of them on the right of the greater than. And so maybe I should write this down. So you're looking at greater than. You put one of your numbers on the left and one of your numbers on the right, right? And either this is a true statement or a false statement, right? So if you have, say, 2 and 1, you put them down in on 2 on the left and 1 on the right of your greater than. This rings in your head as a true statement, right? But if you were to put in 1 and 2, that rings as a false statement, right? So this x less than y, this can be either true or false. So you have this kind of input of a pair of your objects. You put that into this relation and you get either a true or a false value out of it. So the basic answer to this question, is that these relations distinguish certain ordered pairs of elements of a set. And that is the ordered pairs for which the relation is true. So just to take some examples, and so for the relation less than, I already saw, so for like 3 and pi, right, you get a true value here. But for, if you put in pi squared and e squared, you get a false value. So 3 comma pi is distinguished by this relation. So if we look at equals, right, of course, something like -1, that would give a true value, so that would be distinguished under this by this relation, whereas like -2, that would not. And so sort of this pair is not picked out by this relation as special. Divides, so 5 and 10, right, that would be a distinguished pair under this relation. But something like 7 and 6, that would not be. Right? And it might even be useful to notice that even if we take 5 and 10, which is distinguished by our relation, that flipping them around, right, that is now not distinguished by the relation. Okay, and take something like equivalence mod 3. So 16 and 22. 16 minus 22 is negative 6, and that's divisible by 3. So that would be distinguished by our relation. Also 22 and 16, right? So this time if we switch them, 22 minus 16 is now 6. That's still divisible by 3, so that's distinguished by our relation. But say 7 and 3 are not. And also the reverse pair, 3 and 7, also not. Okay. So the basic idea here is that a relation on a set A, this gives rise to a subset let's say R, of A times A, the Cartesian product of A with itself. So a relation distinguishes a subset of ordered pairs of A, coming from A. Right? And so those would be the ordered pairs for which the relation is true when you substitute that ordered pair in. And essentially what we're going to do is make this our definition of what a relation really is. So a relation on a set is going to be nothing more than a subset of the Cartesian product of the original set with itself. And intuitively, why this move makes good sense is so you can imagine, like, if you're given, so let's say you have some set of numbers. So it probably helps to be concrete about this. So let's sort of, as an example, take our set A to just contain the numbers 1, 2, 3, and 4. And let's look at the following subsets. So I'm just going to write down a subset of A cross A. So R here is going to be this subset here. Just bear with me. Now, as far as you might be concerned right now, I just sort of wrote down a random subset of A times A. Right? But if you look a little bit harder at this subset, what you'll notice is that every one of these pairs, the first number in the pair is less than the second number in the pair. So the remarkable thing is that just looking at this subset of A cross A here, you can kind of discern that the meaning of this subset. So what this subset is sort of expressing is the idea of an element of A being less than another element of A. Right? So we can look at, so we can take our R here and we can reconstruct, so we can reconstruct the meaning of the relation. So of the relation behind it, which is in this case, it's just less than. So a kind of mental exercise you might like to do is for the relations that we started looking at in the examples up here, equals, less than, greater than, divides, equivalent mod n, etc. Is if you look at those relations and then think about the subsets of A cross A that they give rise to, and then just think about those subsets. Convince yourself that you can mentally reconstruct the original, like the sort of meaning of the original relation that was behind those subsets. That really nothing is lost by just throwing away the the original mental model you had of this relation and replacing it purely with the subset R itself. So that sort of exercise, if you can do that exercise, and I claim that you should be able to do that exercise, that legitimates this idea of replacing our sort of intuitive notion of these relations with just the notion of a subset of a Cartesian product. Okay, and so that sort of mental exercise there, the success of that mental exercise there leads to the following definition. So definition, a relation on a set A is a subset R of A cross A. That's it. And so we write, so that's the definition, and then just a little bit of notation. We write X, R, Y, and read that X is related to Y for X comma Y in R. And so if the ordered pair XY is in that subset, then we'll write that X is related to Y as X capital RY. And X capital RY exactly just means, in terms of this definition, that the ordered pair XY is in that subset R. Okay, so let's take a look at some more examples. And I'll just use the set that we used above, 1, 2, 3, 4. So let's look at the subset that corresponds to the relation greater than or equal to. So that's going to correspond to the subset R of A cross A, like this. So 1 is greater than or equal to 1, but it's not greater than or equal to anything else, right? And then 2 is greater than or equal to 2, and it's also greater than or equal to 1, and so much for 2. And then 3 is greater than or equal to 3, is greater than or equal to 2, is greater than or equal to 1, and that's that for 3. And then 4 is greater than or equal to 4, it's greater than or equal to 3, it's greater than or equal to 2, and it's greater than or equal to 1. Okay, so we have we have a 10 element subset here, 4 plus 3 plus 2 plus 1. And so this 10 element subset of A cross A, that is equivalent to the relation greater than or equal to on the set A. And again, if you just look at the set itself, the set R, and just looking at all of these pairs, you should be able to mentally reconstruct the meaning of the original relation just by looking at the pairs of elements, right? So just looking at the pairs of elements, you should be able to sort of discern the hidden meaning behind this particular set of pairs. All right, so there's nothing lost by just defining this relation greater than or equal to on our set by this subset R of A cross A. Okay, so again, using A is 1, 2, 3, 4, we can look at, so we can define another relation. So we'll just say it in words as same parity. And same parity, that's really equivalence mod 2. And so two numbers have the same parity means that they're either both even or both odd, and in either case their difference is divisible by 2. So that's what equivalence mod 2 means. And that is going to be equivalent to the subset. So 1 and 1 have the same parity. 1 and 3 have the same parity. 3 and 1 have the same parity. So you have to be careful here that our elements here, they're ordered pairs, right? So 1, 3 is different than 3, 1. And so it makes, the order makes a difference. The order counts. So 1 has the same parity as 3 we should count that as different than saying that 3 has the same parity of 1. Okay, and then 3 also has the same parity as 3. So those are the odds, and then we have the similar thing for 2 and 4. Okay, so that 8-element subset there, that corresponds to equivalence mod 2 or same parity, that relation. And we'll see one utility of this set model is that we can combine relations in a natural way. So let's consider the relation. So our relation is going to be x is greater than or equal to y, and x has the same parity as y. And this relation, well, x is greater than or equal to y, so this is logically equivalent to, so x is greater than or equal to y. Oh, I just realized something. I should have named that set there something different because I used r in the first example. So let's just call that s. And so back to our current example, x is greater than or equal to y. That's the same thing as saying that xy is in that set r above there, right? And x has the same parity as y. That's equivalent to saying, so this is going to be and x, y is in the set S from the second example above, right? But xy is in R and xy is in S. That's exactly the same thing as saying that xy is in the intersection of R and S, right? So combining two relations into the compound relation, the relation 1 and relation 2 holds, corresponds to intersection of sets. And so basically x, r, y, and x, s, y, that's the same thing as x, r intersect s, y. So that's one nice natural feature of our definition. So let's take our set 1, 2, 3, 4 again, and let's just ask how many relations on A are there? Well, a relation on A is just a subset of A cross A, right? So this is just the same thing. This is equivalent to saying how many subsets of A cross A are there. And so this is just how many elements are in the power set of A cross A. And that's something that we've computed this type of thing before. So the cardinality of the power set of A cross A. So the cardinality of the power set of a set, that is 2 to the cardinality of the set itself. And the cardinality of a product set like that is just the product of the cardinality. So this is 2 to the cardinality of A squared. And the cardinality of A is 4, so this is 2 to the 16, right, which is rather large. So one point to make here is that you'd probably be hard pressed to assign a meaning to each of these relations, right? So any one of these random 2 to the 16th subsets of A cross A constitutes a relation on our set A. And now, I mean, our initial examples of relations came from, sort of meaningful relations that we've come to understand through experience and time over the years. But I think you'd be hard pressed to assign some kind of meaning to these 2 to the 16th relations on this simple set A that we have here. So this is kind of a common thing that happens in math. You have some examples of a phenomena, like in this case relations, and you want to sort of see what's common among those examples. You want to define some general notion, and you define your general notion, and you keep it as simple and natural as possible while retaining all the features that you want. But you often find that lots of sort of extra, sort of more stuff ends up appearing than you might have expected initially. So along with all of our natural examples of relations, now we have all of these, potentially quote unquote meaningless relations popping up because we've just defined relation to be this rather natural though general notion of just a subset of A cross A. So this is kind of bound to happen. So we kept things simple in our definition, and therefore we have to contend with the fact that there's a glut of examples now of our concepts, which don't really seem to have any natural, intuitive meaning to them. But that's just kind of how things tend to go often in math. Try to keep things simple, and then you end up with sort of more than you expected. Okay, anyway, a couple more examples. So equality on a set A, that corresponds to the subset of A cross A. So that corresponds to the subset D, which is just the set of all x comma x, where x is in A. So this, the D, sometimes this is called the diagonal subset of A cross A. So that's what the D stands for. And another example, less than, so if we look at less than on Z, this corresponds to, so if X is less than Y, so how do we express that? So usually we would express X is less than Y by saying Y minus X is greater than 0. But that, it seems kind of weird to define less than in terms of greater than. So we should try to be somewhat less circular about our definition. So one thing we can say is that, when X is less than Y, then Y minus X is a natural number. So we'll say that. And so when Y is greater than X, Y minus X is not 0 or negative, right? So it's a natural number. So that's one way of defining our set. So this would be our relation set there. Okay. So as I was saying in the example up here, our notion of relation is very general. It captures all the examples we want in just the right way, but it turns out we're kind of letting quite a lot in under the door. with our definition just allowing it to be any subset of A cross A. So it's kind of hard to say anything specific about, it's hard to say anything interesting about relations with a definition that general. So what we want to do is kind of identify some special properties that the more familiar relations, the more natural relations that we're used to have. So for example, if we think about less than or equal, equal, and divides, if we think about those three relations, they all have a special property. So they have the property x is related to x. And so we know that x is less than or equal to x, that's always true. X is equal to x, that's always true. X divides x, right? And this is all for appropriate x, for which these relations make sense. That these are always true properties, right? But for example, less than does not have this property. And because x less than x is never true. Another special property that some relations have, so for example, like equality or inequality, not inequality, not equality, not equal, and equivalence mod n, they all have the property that if x is related to y, then y is related to x. So they have the property that x related to y implies y is related to x. Okay, so x equal to y, that implies that y is equal to x. If x is not equal to y, that implies that y is not equal to x. And if x is equivalent to y mod n, then y is equivalent to x mod n. And this is because x minus y, if that's divisible by n, that's n times k, then y minus x is n times negative k. So that's still divisible by n. But for example, x less than or equal to y does not have this property. So less than or equal to does not have this property. Because, for example, 4 less than or equal to 5 does not imply that 5 is less than or equal to 4. And so for some x and y, this is true. So if x equals y, then x less than or equal to y and y less than or equal to x are both true, but it's not true for all x, y. And the last type of special property is one that's shared by less than or equal, also greater than or equal, divides, and equals. And these all have the property. So they have the property. It's a property called transitivity. So the property that if x is related to y and y is related to z, then that implies that x is related to z. Right? So if we know that x is less than or equal to y and y is less than or equal to z, we know that implies that x is less than or equal to z. Right? Or that if x divides y, and so if x times something is y and y times something is z, then x times something is z. Right? Just the product of the two somethings in the original two, so x divides z. And of course the easiest one is if x equals y and y equals z, then x equals z. Okay. So here's the definition. A relation R on a set A is called, one, reflexive if X is related to X for all X in A. Okay, so you think about reflection in the mirror. You look in the mirror, you see yourself, so that's the X related to X. Two, called symmetric, if X being related to Y implies that Y is related to X. So if this is true for all X, Y in A. And three is called transitive. If X is related to Y and Y is related to Z, implies X is related to Z is true for all X, Y, Z in A. So let's look at a simple example. So we just look at a three-element set, 1, 2, 3, and we consider the subset of A cross A, which just contains 1, 2, and 2, 3. It's easy to see that actually this isn't reflexive, symmetric, or transitive. So this example shows that a relation doesn't have to satisfy any one of these conditions. So R is not reflexive, symmetric, or transitive. So, for example, for the reflexive part, so 1, 1 is not in R. And so that says that that's equivalent to 1 is not related to 1. I should have introduced this notation before. If you want to say that X is not related to Y, you write X, R, Y, but then you put a slash through the R. So we don't have reflexivity. Symmetric, for symmetric, so 1 is related to 2. So let me write it that way. So 1 is related to 2, but 2 is not related to R. Or sorry, 2 is not related to 1. Right? Because 2, 1 is not in that set. So that's not symmetric. And for transitive, we have 1 is related to 2, and 2 is related to 3, but 1 is not related to 3. Okay, so you don't have, your relation doesn't have to satisfy any one of these conditions. And it's not hard. I mean, you can easily come up with examples of relations which have, any one of these, whatever combination of properties you want. If you want a relation which satisfies 2 of these properties and not a third, you'd be able to find that. Or one of these properties and not the other 2, you'd be able to find that. So this might be a convenient place to introduce pictures into this. So sometimes when you have small sets and small relation sets, it's easy to draw a picture that sort of summarizes the relation. So in this case, our set has 3 elements. And for every ordered pair in our relation, we just draw an arrow from the first one in the pair to the second one. So 1, 2, that's in there. So we have that arrow, and 2, 3, that's in there. So we have that arrow. And that's a complete picture of our relation in this case. And so we can actually see from this picture that that our relation has none of the required properties. Because, so graphically, what reflexive looks like. So reflexive basically means that if you have an element of your set X, that you must also automatically have an arrow pointing from X to itself. And so you have to have XX, right? So you must have an arrow pointing from X to itself. Symmetric means that if you're looking at an arrow from X to Y, that automatically must mean that the reverse arrow is there. So actually it's not a single arrow, it's a double arrow, a back and forth arrow. And transitive means that if you have a triangle like this, that you have to have the third side of the triangle where the arrow is directed. And so if you've traveled from X to Z with Y as an intermediary, you must also have the direct trip from X to Z. Okay, so we can see immediately in our example up here that we have some problems if we just look at the picture, right? Because we have dots without the loops at them, right? So we don't have, say, this loop at 1 there. So our relation can't be reflexive. Our arrows are not double arrows, so this can't be symmetric. And we have a trip from 1 to 3, but not the direct trip from 1 to 3. And so 1 to 3 with 2 is an intermediary, but not the direct trip from 1 to 3. So that can't be transitive either. Okay, so sometimes those pictures are useful. So for example, so let's look at another example. So we take A to be a set just composed of 4 symbols, B, C, D, E, and I'll write down the relation. Okay, so there's the relation set there. And let's try to see whether it's reflexive, symmetric, and transitive. So reflexive, symmetric, transitive. So for reflexive, we would need to have x related to x for every x in A. So we see that we have B is related to B, we have C is related to C, and we have D is related to D, but there's no E related to E. Right? So E is not related to E, so it's not reflexive. So the answer is no here. As for symmetric, it's pretty easy to see. So anytime you have a pair, so like for example B and C here, you have the symmetric pair CB. And for BD, you have the symmetric pair DB. And for CD, you have the symmetric pair DC. So it's easy to see that, yes, it is symmetric. The transitive, that's a little bit harder to determine just by looking at the elements of the set. It's a bit annoying, but what really helps is the picture here. So so let's look at the picture. So I'll just mock up a picture first. We have BB, we have BC, we have CB, we have BD, we have DB, we have CC, we have CD, we have DC, and we have DD. Right, so the E without a loop at it, that exposes the non-reflexivity. The arrows being all double arrows, that tells us that we have a symmetric relation. And it seems pretty clear from this that we have a transitive relation as well. So for any trip of two steps, so from C to D, right, we can go along this. So we can go like C to D like that, but we also have the direct trip right there, right? And also from so we can do a similar trip from B to C, or from D to C, or from C to B, and in any case we have the third leg, right? So basically, we have every leg of this triangle in here. So our relation is going to be transitive. So yes to transitive. Whoops. Because we see that whenever we have two legs of a triangle, we have the third in the picture. So see picture. All right, so that gives us an example of a relation which is symmetric and transitive but not reflexive. And right, so that's not really a great proof that our relation is transitive, but it's much easier to, in general, it's easy to check a relation is transitive if you sort of know the meaning behind the relation, so that the defining property of the relation. So in this case, so the defining property of our relation of R is that X and Y, so X, R, Y, let me say it that way. So X, R, Y means X and Y are consonants. They're not vowels, so neither of them are vowels. So that's why we have, so the only vowel in our set is E. So B, C, and D are consonants, and so we have all of the possible pairs that you can make with B, C, and D. BB, BC, BD, and the reverses of all of those, and CC and DD. Yeah, so with this, it's pretty clear that we have a transitive relation, because if X is related to Y, so X related to Y and Y related to Z, this just means X and Y are consonants and Y and Z are consonants. And of course, that implies that X and Z are consonants. And that's exactly to say that X is related to Z. So having our relation defined, so having our set R defined by some property can make it much easier to determine that a relation is transitive than just having the set presented to you explicitly. All right, so let me give you a quick reminder here. Just so we're clear. A is equivalent to B mod n. So n here is a natural number. That exactly means, so this is equivalent to A minus B is divisible by n. A minus B divisible by n. N divides A minus B. Okay, so here's a proposition. So what we'll prove is that the relation equivalent mod n is a reflexive, symmetric, and transitive relation. So proposition, if n is a natural number, then equivalence mod n is a reflexive, symmetric, and transitive relation on any subset of Z. Okay, so here's the proof. We'll check reflexive. So we need to check that A is equivalent to A mod n, right? So that just means that, to check that A is equivalent to A mod n, we need that n divides A minus A, but A minus A equals 0, and n divides 0, obviously. So that's so much for the reflexivity. So check the symmetry. So we assume that A is equivalent to B mod n. And what we want to show is that B is equivalent to A mod n. Right? So A is equivalent to B mod n, that is that n divides A minus B. So A minus B is equal to n times k for some integer k. And, well, we're trying to say that B is equivalent to A mod n, which just means that B minus A is divisible by n. And so we'll just take this equation here and write it in terms of B minus A. So this is equivalence. This is the same as B minus A equals n times negative k. Right? So n divides B minus A, which just means that A is equivalent to B. Just means B is equivalent to A, mod n. Okay, and then 3 is we'll check the transitivity. So for this, we assume that A is equivalent to B mod n, and that B is equivalent to C mod n. And what we need to show is that A is equivalent to C mod n. Right? So what we need to show is that n divides A minus C. So what do we know from these modular equivalences? So this means, so I'll just cut right to the point. N divides A minus B. That means that A minus B equals n times k for some integer k, and that B minus C is equal to n times L. So this is for some integers k and L. And what we want to know about is A minus C. Right? We want to say that A is equivalent to C mod n. So A minus C, that is, well, we just want to rewrite that in terms of A minus B and B minus C. Right? But if we just take A minus B and add B minus C, we get A minus C. Right? So this is equal to A minus B plus B minus C. And that is n times k plus n times L, which is n times k plus L. So we see that A minus C is divisible by n, and thus n divides A minus C, so A is equivalent to C mod n by definition. Okay, and that completes the proof. So so equivalence modulo some natural number n bigger than 1. Maybe I should have said that here. Yeah, so our n here is bigger than 1. N is an n bigger than 1. So our equivalence mod n, for appropriate n, is reflexive, symmetric, and transitive, so it has all three of the properties. So we've seen examples of equivalence relations that have a variety of combinations of the properties. Okay, and any relation which has these three properties is called an equivalence relation. So definition: an equivalence relation is a relation on a set A which is reflexive, symmetric, and transitive. So let's look at some examples. So let's take A to be our set with 4 elements, 1, 2, 3, 4. So let's say we have our elements of our set arranged like this, visually arranged like this. So if we have an equivalence relation, our equivalence relation, first of all, it has to be reflexive, right? So we have to have an arrow pointing from every point to itself. Right? And if we just stop there, then actually we have a relation which is symmetric and transitive as well, right? Because we don't have any arrows pointing from one point to another, for which we would need to have a double arrow, and we don't have any journeys from any point to another point with a waypoint in between, for which we would need the direct journey, which would be the transitive property. So all the symmetric and transitive properties kind of collapse to trivialities when you just have these loops at each one of your points. And so this is an equivalence relation, and to really convince yourself that fully that it's equivalence relation, just notice that this is the same as this expresses the relation of equality, right? So the subsets here are just 1, 1, 2, 2, 3, 3, 4, 4. So this is just the relation of equality on our set. Okay, so another equivalence relation. So again, we have to have all of our loops here. And then we can have a variety of, so that was just so we're sort of starting from the simplest possible equivalence relation. So the simplest one is where you just have loops at every point and nothing else. Now the next step up is to add some arrow that goes from one point to a different point. So if we add the arrow that goes from 1 to 2, well, then the symmetric property demands that we have to have the reverse arrow. But if we just stop there, then that is an equivalence relation. Right? So it clearly is reflexive and symmetric, and again, there's no journeys here that you can take from with two stops along the way. So there's nothing non-trivial to verify for the transitive property. And you could also have so instead of that one, you could have a diagram that looks like this, and you could have the arrow going from, say, 1 to 3, and then the arrow going from 3 back to 1. But in some sense, these are really kind of the same diagram. If we just sort of relabel our points, so if we just change the label of this point from 3 to 2, so we interchange the labels for 3 and 2, then our diagram will look the same as the one that we drew before. So in some sense, we're not seeing anything really new with that diagram. So we'll have to add more than one non-trivial arrow to see something interesting. So again, we draw all of our loops to make sure we have a reflexive relation. And now let's draw our first arrow connecting two different points. And let's say I draw that we're from 1 to 3. We have to have the arrow going back. And let's, in this diagram, let's add a second arrow for the first time. So one thing we can do is we can add an arrow that goes from 2 to 4, and then of course we have to do the one going backwards. And that would make to be symmetric. And so this is actually an example of the same parity relation here. So this is the relation that expresses the same parity. And we can have a very similar sort of equivalent looking diagram. So there's more than one way to put, so for example, if I take 1 to 2 and 2 back to 1 and 3 to 4 and 4 back to 1, that's a different equivalence relation, but in some sense it looks a lot like the equivalence relation that we just drew. It's kind of, right, if we just sort of change the labels on the points, it would in some sense be equivalent to that equivalence relation. So not really, the diagram doesn't really look any different. So to get a different looking diagram with at least two non-trivial arrows. So again, you draw your loops. And let's say this time, so we have our first arrow going from 1 to 3, and then of course we have to do from 3 back to 1. And instead of going from 2 to 4, let's make our second arrow go from 1 to 2. And then of course we have to have 2 back to 1. But now see, for the first time, we can get from one point to another point with a stop in between. So for example, here we can go from 3 to 2, stopping off at 1 in between. And in order for this to be an equivalence relation, we therefore have to have the arrow that goes from 3 to 2. And once we have that arrow, we have to have the arrow that goes back from 2 to 3 directly. And now we have all of the sides of that triangle, so this diagram is going to be transitive as well as symmetric and reflexive. So this is an equivalence, a diagram of an equivalence relation here. So those are essentially the only ways you can add two arrows. So you have two arrows here, two non-trivial arrows here, and then if you try to add two non-trivial arrows in a different way, you end up having to add a third because of the transitive condition in that picture. And so then it's the case that if you try to look at any bigger equivalence relation here, so again, if we draw our first arrow, our second arrow, so for our second arrow, so we start with the diagram that we just drew. If we add any other arrow, so for example, if I add this one here, then I have to add, so I can get from 1 to 4 on a journey of 2 steps, so I have to be able to go directly from 1 to 4 and back. And now I can get from, let's see, so now I can get from, from 4 to 2 on a 2-step journey, so I have to be able to go directly from 4 to 2 and also back. And now that's every possible arrow going from one point to another. So I can't, so I can't add any more arrows. That's kind of the maximal diagram. And if instead of starting with that one edge, if you start adding a different edge, like so if you add this one, then the same logic applies. So now you can get from 4 to 3, so you have to be able to get there directly. And now you can get from 4 to 2, so you have to be able to get there directly. And so no matter what you do, if you add a new edge to this diagram here, you end up at this picture here. And the same is going to be true of this picture up here. So if you add the edge, say from 1 to 2, you have to add the reverse arrow, and now you can get from 3 to 2 in 2 steps, or you can get from 1 to 4 in 2 steps, right? And then you can get from 3 to 4 in 2 steps, so you have to be able to get there directly, and then that leads again to the diagram down here. So basically, what we had before. So these are basically sort of all of the sort of pictures of equivalence relations that you could possibly get, up to relabeling the points differently. And so before we end, I would just want to give you a kind of taste of where we're going. So equivalence relations are important because they correspond to what's called a partition of a set. So let's see. So let's say this is diagram 1, this is 2, this is 3, this is 4, and this is 5. So what you can notice here in diagram 1 is that our set A has been split up into 4 parts, right? So you have the part which, so you just have the element 1, the element 2, the element 3, and the element 4. So those elements, they're only connected to themselves by arrows. They're not connected to each other by arrows. So by contrast, in the second picture, we have 1 and 2. Those are connected, and 3 and 4 are all by their lonesome. So we have 3 parts here. In the third picture, we have just 2 parts. 2 parts, and they each have 2 things in them. Whereas for the fourth picture, we have two parts. One has three pieces, three elements, and the last one just has one. And in the final diagram, everything is connected to everything else, so we just have one big chunk. So the first picture corresponds to taking our set A and writing it as the set containing 1 union the set containing 2 union the set containing 3 union the set containing 4. And the second part, the second picture, that corresponds to taking our set A and writing it as the set containing 1 and 2 union the set containing 3 union the set containing 4. And then the third picture corresponds to writing A as set containing 1 and 3 union the set containing 2 and 4. Number 4, our set A, the picture corresponds to writing our set A as 1, 2, 3 union 4, the set containing just 4, and 5 just corresponds to A is just equal to A, so the set containing 1, 2, 3, 4. Right, everything all bunched together. So what we'll see later, we'll prove later that equivalence relations on A, they correspond exactly to what are called partitions of A. So they correspond to ways to break up the set A into disjoint, so non-overlapping subsets that cover all of A. And this is a surprisingly pervasive and important notion as you continue forward in mathematics. You'll see it all over the place. So this is a very important notion to absorb. And this is sort of the fundamental theorem on equivalence relations, is that they correspond to partitions of your set. Okay, that's all we have time for now.